So yeah, I'm actually going to do live coding as well. Not in the same sense, I'm afraid. I'm sort of imagining a future talk where I do live coding via live coding in Idris, and that will be, I mean, I think that's my new career goal. Because David, you were obviously having enormous fun there, and I was having enormous fun too, playing along. And that's the rest of my week gone. So anyway, so yeah, I saw a couple of hands go up when Zishan was asking who knew Idris, and I'm kind of glad there weren't too many hands went up. Firstly, because you have nothing to unlearn, and secondly, because I've kind of worked under the assumption that this is an audience who is familiar with functional programming concepts. Is that reasonable to say? So you know about higher order functions. You've learned some of these details from Shriram this morning, of course. But you haven't necessarily seen dependent types, or what I'm going to talk about here, quantitative types. That's my assumption about the audience going into this talk. My goal for this talk is that by the end of it, that you will know what this title means, and if we get that far, then we've succeeded. Right. So I'll tell you a little bit about Idris just to set the scene. So Idris is the programming language that I've been working on since goodness knows when, as long as I can remember. So 2008, something like that. And it started because I started working on it because I just wanted to see. I wanted to see if dependent types, which I'll talk about a little bit more, were a reasonable way of building a practical programming language. Since then, I've completely lost or changed my opinion of what practical even means. I don't know what the word practical means anymore. I'm just going to leave that to the audience to decide if there is anything practical about this. But let's just say I'm trying to do something general purpose that makes programming fun. So it supports. I think the key thing about dependent types, that just to keep in mind throughout, is that types are first class in the language. So if you've done a bit of functional programming, one of the things that people will tell you when they're teaching you functional programming is that functions are first class. First class meaning kind of informally, you can assign them to variables, you can return them from functions, you can pass them from functions, all of that. So if your language has first class types, then you can assign types to variables, pass them to functions, return them from functions, and so on. So you can compute with types, and there's not any more a syntactic distinction between types and values. And we're going to see throughout this talk how that all changes the way we think about some kinds of programs. And this new version, basically, yeah, maybe 5 or 6 years ago, I'd got Idris to version 1. It was kind of working okay. We were able to try out some interesting things with it, and I thought I want to scale this up and see if I can write some realistic-looking programs, or I can write some programs of reasonable scale. So what should I implement? And I realized two things. Firstly, Idris 1 was just far too slow to do anything interesting with it, and secondly, I don't actually know how to write any other kinds of programs. So the only reasonable thing to do was have a crack at implementing Idris in itself. So the end result, I put these numbers on the slide just because every time I give this talk, all of the numbers go up, and it's interesting to see how it changes over time. But also to give you a sense of scale, that it's a reasonably sized project. It's able to compile itself, and so that's just the rite of passage for a programming language, I suppose. And there's enough libraries with it, and it's kind of the performance is reasonable. Built on quantitative type theory, and I'll give you a rough idea of what that means up front. So when you write your APIs with types, or when you give the type of a function or the type of a variable, that type is, ask 100 programmers for a definition of type, you'll get at least 100 answers. So I necessarily come up with a definition of type. But that type is there to say what the program is supposed to do. In a kind of very vague sense, it's a kind of a plan for the program. So dependent types first-class types give you a bit more precision in explaining upfront what the program is supposed to do, and then bringing in quantitative types, what that's going to do is allow us to have a bit more precision in when the program is allowed to do it. So conventionally, types are about what, quantitative types, they're going to be about when. And that when might be now or later or once or never, and that's the thing to keep in mind. Now, I think the best thing to do is just do some, you don't need to see me reminding myself about things. I'll start with just a warm-up example so that you've seen some Idris code that is doing something that is familiar to. I'm sure you've all written codes to append to linked lists. I want to give you a sense of how we work on programs in Idris. So this is type-driven development. I like to call it type-driven development by analogy with test-driven development. And there are some similar concepts going on. And I suppose the main similarity is this encouragement to think about what your program is going to do before you're, again, looking back to Sriram's talk, think about what your program is going to do before you start working on the program. You can do that with examples, you can do that with tests, you can do that with types. Here we're going to do it with types. We've got a type signature, so we can write type signatures without a definition, and Idris will happily compile that, and you'll get a runtime error if the program is incomplete. One of the principles here is that programs spend most of their time in an incomplete state. So the majority of, as programmers at least, the majority of time you spend with a program, it's with an incomplete program. And it's quite useful if your compiler will help you along with that. While your program is incomplete, your language implementation still knows an awful lot about your program. So you've compiled it, it's done a lot of syntactic and semantic analysis on it. So it knows about the types of various expressions, various variables, and I don't think the compiler should keep that to itself. You know, the compiler knows these things. You write the program, you get an error message, which is essentially the compiler saying, ha ha, I know something you don't know. And one of the many principles of type-driven development is it shouldn't keep that to itself. So we can think about programming not so much as writing down a complete incantation, feeding it to the oracle or feeding it to the teacher, who then says, ha ha, no, you've got it wrong, see me after class. Rather, we should think of the compiler as being our lab assistant, where I've written down the type and I say, here's what we're going to work on together. And the machine says, okay, how can I help you? So I'm just going to interactively write this program. I'm doing this inside Vim because I'm like that. But there are other editor modes. So VS Code, I think, is what all the cool kids use these days. Emacs as well. So if I ask it to give me a skeleton or candidate definition, that's what I've got here. This thing with a query you see on the right-hand side, this is, I should say, just for the sake of those who aren't familiar with Idris, this is, we're defining programs in terms of recursively defined equations. So if you've seen any Haskell, who's seen Haskell? Yeah, most of you, good. Or ML or any kind of that form of language, recursively defined equations. And we can leave holes for things we haven't written yet. If we have a hole, we can ask the machine to tell us things about the hole. So it will tell me, what have I got? Well, I've got y's is of type list of A, x's is of type list of A. Types are first class, so A is of type type. What's the type of type? Type of type is type 1, the type of type 1 is type 2, and so on. Goes on forever. Don't worry about it. We lied all of that stuff. And the thing we're trying to get to is also a list A. So there's a mysterious 0 here. I'll come back to that. We'll just finish this definition. Another thing I can do is ask the machine to give me all of the possibilities for one of these variables. So lists are defined as either nil or a cons cell. So it's either empty or it's a head and a tail. So I'm going to ask it to do a case split on the first argument. Gives me two possibilities. So in this first case, I've only got y's now. I'm trying to give a list of A's. Oh, so I'm trying to get a list of A's, and I've got a list of A's. So I think there's two possibilities for this. It could either be the empty list, a list of anything, or if it's going to be a non-empty list, the only thing it could possibly be is Y's, because I don't know anything else about A. So I actually just asked it to search for that, and it picked Y's. And then in this third case, I'm just going to fill this in. And I'll reload that just to make sure. Good, that's good. So far, so familiar, hopefully. All making sense so far, yeah? Here's a fun thing I can do, just as an aside. I'll delete all of that. Something I'm going to use just a little bit in this talk is a built-in type-driven program synthesis mechanism. So it's fairly basic. What it does is, if I ask the machine to generate a plausible-looking definition from the type, it will essentially do what I just did, which is invent a candidate definition, do case splits, do searches for plausible things that fit the hole on the right-hand side. It will do that. It will search through... I think it's, if I remember rightly, it comes up with either 16 candidate definitions, so a nice round number like 16, or it stops after 1 second, and then it picks the most likely one, where the most likely is defined by, does it use all of the inputs? Which is, this, by the way, I'm going to call that an algorithm, in the sense of a thing where I can explain exactly what it does and know what result it's going to get, which is apparently not what algorithm means anymore. However, there we go. So I asked it to generate it. It actually did come up with append, which is quite pleasing. I asked ChatGPT to. I've got to mention ChatGPT. It's. I can't really get to this point and not mention LLMs. ChatGPT also comes up with this definition, but I think it probably does it by web search. Another thing I can do if I don't get the thing I want, I can sort of repeatedly hit it with a hammer. And this is just giving me lots of other plausible looking. I mean, none of these are really append, are they? But I mean it's valid. It's anyway. Let's just use the one it first thought of because it happened to be correct. Okay, now first-class types are when things get a bit more interesting. So if I want, let's say, a type synonym, a type def, I don't need a special syntax or a special feature in the language for type synonyms because I can write functions that compute types. So this one's a teensy bit contrived, but I'm just going to go with it anyway. I'm going to take a Boolean as an input, and I'm going to pick a type. I'll pick one type if it's true, one type if it's false. So if it's false, let's have strings, let's say, and if it's true, let's have integers. Now, why would you ever write a function to compute a type? What's it for? Well, where do you use types? So you use types as part of bigger types. So here, again, a teensy bit contrived, but I'm going to convert from one type to another, and the type I'm converting from is going to be given by this first argument. So here we're going to see, I think the sort of probably the biggest thing to understand about first-class types, or about dependently typed programming in general, is that once you are allowed to express relationships between values and types, you can then start learning things about one part of your program from the behavior of another part of your program. So you can learn about, you can reason about which branch of an if-then-else you've gone down. Or you can say, well, the input here was a Boolean, therefore I must be expecting a string now. There is kind of a very familiar mainstream example of this concept, which is printf. So printf, you've got a format string. That format string tells you what the type of the rest of the inputs should be. So you probably have seen this before, just not in this sense of being baked into the language. Okay, so if I look at the type of this right-hand side now, it says, okay, we've got something of type make type X. We want something of type make type not X, but I have no idea what these types are. And the way we'll find out what these types are is by pattern matching on the Boolean. So if in the case where the Boolean is false, if I check that right-hand side now, okay, it now knows more about what we're supposed to be doing. We've looked at the first argument. That means we've learned something about the second argument, and so we've learned something about the return type. So we're doing a little bit of type level computation here, so symbolic computation on the type to work out what the inputs are actually going to be. And I'm not going to complete this definition because hopefully you get the idea from that. Just one maybe realistic example of that where you might use something like that. I've never actually done this in practice, but maybe you have you've got a dictionary, and in the case where the dictionary is small, whatever that means, 3 or 4 entries, maybe you'll just use an A list, so pairing strings with values. And if the dictionary is bigger, maybe you want something a bit better, like this sorted map is implemented as a I think it's a red-black tree internally. So it's a balanced tree internally. So you might want to compute the type that you're using for a data structure at runtime based on information that you don't get until runtime, but you want to reason about at compile time. So this is allowing us to reason about what's going on at runtime using information we only know at compile time. So that is... Yes, oh, I should have said this. I will take questions anytime you like. Just shout out. I'll repeat it for the sake of anyone who so that Zishan doesn't have to run around the room. So go ahead.
Could you go back to the code you had a moment ago?
Yeah.
Because I'm trying to figure out, so if you scroll down to the bottom, to the dictionary example.
Yeah.
What's going on with the braces?
Oh, what's going on with the braces?
The insert line.
Yeah, what's going with... do you know what? I'm going to defer that because it's a really important question, and it's so important that I even plan to talk about it. See, I did plan this. Who'd have thought it? Okay, so I'm going to talk about it in the context of actually when we get to quantities, because we need to know about quantities to know what's going on with the braces. So, tell you what quantitative type theory is. It's a lovely little It's a lovely calculus designed by, well, it is quite little actually. Let's be honest. It is. There's only a few rules compared to many other languages. So it's we're combining linear and dependent types. So dependent types you've just seen. This is first class types. Values can tell you something about types. Linear types. If I can again massively oversimplify, a linear type system is one where every value has to be used exactly once. So if a value can be used exactly once, that means you can start tracing stateful programs, for example. So the way we do I/O in Idris, for example, is we talk about the input world state and the output world state. Now that once I have done an operation on the world, like I've printed a value to a screen, the world has changed, so I can't use that old world anymore. So linear types allow us to reason in that way. Turns out to be quite tricky to come up with a system that combines linear and dependent types neatly. Many efforts have been made. Connor and Bob came up with something that I think is beautiful. And the key idea is that every variable is associated with a quantity. There's lots of possible choices you can make for what those quantities could be. I kept this really as simple as it can. Well, not quite as simple as it can be, but almost as simple as it can be while still being interesting. And my quantities are either 0, that is, which means it's not used at runtime. So remember we saw 0 A of type. That means that type is not available to us at runtime. And then there's 1, which means it's used exactly once at runtime. And then there's this omega, which means it's unrestricted at runtime. So in your usual programming environment, everything is omega because it's unrestricted. If you're a Rust programmer, then it's not quite as simple as that. But in most mainstream languages, you're talking about omega. So what this does for Idris too is it solves a really irritating problem that we've had for a long time and not really had a good solution for until now, which is that when types are first class, and therefore when values are allowed to go into types, it's not entirely clear which of those values are going to show up in your program when you compile it and which aren't. And this can be an absolute disaster for performance, because your program might end up computing things that are only really interesting in terms of reasoning. If we've got these quantities, I can say, right, the thing I care about reasoning about is not available at runtime, and then the type system will tell me that it's the type system will guarantee that I'm not doing needless computations. So this zero quantity is really useful. It's the reason for having quantitative type theory in Idris too. This one quantity, however, is far more interesting. And so zero, I use a zero quantity all the time. I wouldn't be without it. It's fantastic. It allows me to know what's happening at runtime. One, I play with this all the time. It's lots of fun to see what we can do with it. But as we'll see, we're getting somewhere with figuring out how to do things with it. We're not necessarily, found the right answer yet. So let me show you quantities, and in the process, answer the question about braces. So I'm going to do this with, this is my new favorite introductory dependent types example. If you've been to a dependent types talk before, you've probably seen vectors. There are no vectors in this talk. So I know, yay. That's a second. I know how I said I was going to repeat things, but I'm not going to repeat them. Okay. So this is run length encoding. So run length encoding, it's a nice simple compression scheme. It goes back to I think television signals. And for those of you who are playing around with computer paint programs in the 80s and 90s, it's a way of compressing images that don't have too many colors in them. So essentially, you say how many of a thing you've got. And then the thing. What's going on here then is I'm declaring a new data type for run length encoded lists. The type of run length encoded lists is parameterized by a list of something. So this tie is a type. So lowercase, something that begins with a lowercase letter is an implicitly bound type variable. And the meaning of this is going to be that the if I see run length of x's, that means when I uncompress the run length encoded thing, I will get that original list x's. So the idea is that we have a sound, if not perfect, representation of the compressed list. So an empty run length encoding is a run length encoding of the empty list. That's all this is saying. And if I have some number n, a natural number, and some element type x, and I have the rest of a run length encoded structure, then that will represent the uncompressed list, n repetitions of x, and then concatenating more onto it. Now, this isn't a perfect representation because, for example, this n could be 0, and then I've got 0 repetitions of the number. So it's not guaranteeing that it's the best possible compressing, but it is guaranteeing that it's sound. I should, by the way, implement rep. And I'm going to do that the easy way by asking the machine. It's kind of fun that when I do this type-driven synthesis, you're probably thinking, I bet he's only doing the things that he knows works. And you'd be right. Of course I am. I've done this before. Honestly, it's a magic trick. It's a conjuring trick. That's all it is. It is valuable in practice. So particularly if you're doing some kind of boring plumbing, or if you've got a little function that you've written hundreds of times and it just follows the structure, that's what it's pretty good at. And the good news is what it generates, it's going to be type correct. And it doesn't free you from knowing what you're doing. You still have to look at what it comes out with and check that it's the right thing. But it's a handy little time saver. So I've got a test compressed list here. I'm not going to show you compression. What I want to show you is more about the quantity. So I'm going to show you uncompression, partly because the compression is a little bit fiddly anyway. The important thing is the uncompression. So I'm going to make my first attempt at uncompressing the list. So firstly, we've got these braces here. So any of these implicitly bound names, they are arguments to the type, or they are bound as function arguments, but they are bound implicitly. These braces here are saying, right, well, tie was an implicitly bound argument, but I do want to talk about it. So it's just bringing that implicit thing back into scope. because x's has type list of tie, and that's what I want to produce is a list of tie. I'm gonna try generating this just to see what happens. Do we believe that? No, no. Right. So what about? We haven't used n. Now the heuristic for the synthesis is that we try to use everything. The only trouble is here it doesn't know what it's supposed to do with that n. It doesn't really play any part in the rest of the type. Now I think the problem here is not so much that the types-driven synthesis is weak. I think the problem here is that the type hasn't explained what it is we're trying to do. So, it's like, I don't know how many academics are in the Shriram certainly is academic. You've probably had the experience of students coming to you and demanding a more precise specification because they don't know how to solve the problem. That's kind of what's happening here. But before I do, I'm gonna rule out one other possibility. So let's give that a better name. You might think, well, I've already got x's, so I've got the original list here, and I can, well, I have the original list in scope, but you'll see that it's got a 0 next to it, and that 0 means we're allowed to talk about it, but we can't use it at runtime. So this is a thing we can talk about at compile time for reasoning purposes, but not at runtime. So if I blunder on and try, it gives me, well, it says x's is not accessible in this context, which is perhaps an unhelpful message. It's say, x's is not available at runtime. What I can do, one possible solution to this is I can make it available at runtime. So these braces, to answer the question from about half an hour ago, these braces are saying I have an implicit argument x's. Now, if I just leave the implicit arguments unbound, it will infer them, and it'll infer the type, it'll infer that they are an additional implicit argument. But if I say nothing else, it will make the assumption that I didn't intend that to be a runtime thing, and it will say the quantity is 0. If I actually give it and put it in braces, then the assumption is this is unrestricted quantity. So if I've got a function argument, whether explicit here or implicit here, and I don't give a quantity, then the quantity is assumed to be unrestricted. I can be explicit again. So the reason for those syntactic choices, which may seem a little bit mysterious when they first come up, these syntactic choices are made because the most common thing you want to do is the thing that involves the least typing, which I think is a reasonable heuristic for making language design choices. Let's just finish this off though to show how I might write this program how I might give it a more informative type, because it's kind of annoying that I have to write an uncompressed function when I've kind of already written it. It's already in here. This run length type tells me everything I need to know about what an uncompressed list is. But but x's is compile time. So what I'm going to have to do is find a way of promoting that to a runtime value, and I'm going to do it using this singleton type. And because I'm British and in my 40s, I'm going to call the constructor val. And if you know why I've done that, have 5 points. Well done. Some of you clearly do know why I've done that. Okay, so this is a singleton. Then the singleton type is saying that, or the parameter of the type tells you the only thing that the value can be. Now, why would we want that? Well, in this case, the only thing the value can be is x's, because that's the uncompressed list. But there's no quantity annotation here, meaning it's unrestricted, meaning that we will have it available at runtime, which means that the job of this program is to take what we know at compile time about x and turn it into a thing that we know at runtime about x. If I ask it to generate that, it knows. It's in the type here. So I don't have to write that program again. It'd be annoying to have to write that program again. What is slightly annoying is it's put an underscore here. So it puts an underscore if it can infer it. But this is a case of the machine might not need that, but I do. So I'm going to add it. Okay, I'm not going to run this program. I'm just going to take it on trust that this does the right thing in the interests of time. So that's, I hope that's answered your question from 20 minutes ago. So that's what quantities are for. I think it's really, it's in this case, in the case of uncompressed, I think it's vital that we have the quantities that, you know, if this X's accidentally leaks into the runtime program, then I haven't achieved anything by compressing it, because I'd be carrying around the uncompressed and the compressed version. Okay, so let's move on to the linear quantity. And I'm going to do this with an example that I imagine you're all familiar with. These days I use an ATM about once a year because my local barbershop doesn't accept card, and I get a haircut once a year whether I need it or not. But you know, I used to use ATMs, and pretty much how they work is, or how the bank would like them to work, is that they shouldn't dispense money until you have validated, you know, you've entered your PIN and it's been validated, and we're in a validated session. So here's a simplified state machine that shows how an ATM works. So most of the time it's sitting in this ready state, just sitting on the street waiting for someone to insert their card. When someone's inserted their card, it leaps into action. We're in the card inserted state, and at that point it can start doing more things. So it can start taking the input of your PIN. It can check any PIN that has been entered. It can eject the card. So obviously ejecting card doesn't make sense here. Checking the PIN doesn't make sense if the card is inserted. So we're thinking about when we can do things now and not just what we can do. If we check the PIN, that doesn't automatically get us into a validated session because the PIN might be incorrect. So we've got a transition for if the PIN is incorrect and one if it's correct. And then only when we're in a validated session can we dispense money. I showed this to a friend who works at NCR, the cash machine company, expecting to be ripped apart. And so that's a massive oversimplification. He said, "No, that's pretty much how we do it, except we do it in C." So, you know, draw your own conclusions. So there is just to show this is a little bit. There's a little bit of syntax to figure out here. I'll just highlight the most important bits because I'm not here to give an Idris course, but I am here to give you a sense of what it can do. So this L, again, I'm just using a single. I'm using a single letter because I'm a functional programmer, and that's just what we do. But the other reason for using L is because if something is being used a lot, I'm keeping the names short. So L is, in a sense, it's a linearity monad. So it's a way of constructing programs in a linear context and being able to say something about how many times the result is used and how many times the inputs are used. So this use equals 1 in the return type, there's a little bit of monadic magic going on that we don't need to think about here, but it's good to know it's there. That is saying the result of initializing the ATM is an ATM in the ready state that we are allowed to use exactly once. And then inserting a card, we've got an ATM in the ready state. It will give us back an ATM in the card inserted state. We're allowed to use that exactly once. We're using this ATM in the ready state exactly once. So these ones in the annotations are saying that once we have done an operation on that machine, we can't do an operation on that machine again. We can still talk about it. We might want to reason about it. We might want a trace of what's happened that we do at compile time, but we don't have it at runtime. Let's just see that working. And I've just got the types here. I haven't implemented an ATM visualization. Maybe one day I will. But I've got those types written down. Check pin is the interesting one. Did I have that on the? Yeah, I did. Let's talk about check pin. It is worth looking at what's going on here. So when we do these state transitions in the types, sometimes we as the programmer are in control to some extent. So we're in control if the card is inserted. Well, we're saying the card really is inserted. That's an operation that doesn't fail. I suppose the reality is that operation could fail, but I'm saying here that this operation can't fail. Checking the pin, on the other hand, as programmers, we are not in control over whether that pin was entered successfully or not. That is the environment's job to tell us if that was done successfully. And the way I've captured that here is with the machine that we're returning is going to be a resource that depends on the result of a pin check. If that pin check was correct, we move into the session state. If that pin was incorrect, we move into the card inserted state. Now what you see here, if you've been looking at these for ages, they get much easier to read. But as it is, it's a little bit, there's kind of a lot to take in here. And I think it's a lot easier to take it in by developing the program interactively, by developing the program as a conversation with the machine and having the machine help us refine what we know to a complete program. So the first thing I'm going to do is get out my crib sheet, because although I have done this 100 times before, I only forget it when I'm talking to an audience. You've all been there, haven't you? So the first thing we're going to do, I'm going to make a new machine. I'm going to call it M prime for the moment. We are going to insert a card into the machine we've initialized, and we're going to call it M prime. And the reason I'm going to call it M prime is so that you can see what happens. This gives us back a machine with a card inserted that I'm allowed to use exactly once. And now we have the machine M where the ATM was ready. We can still talk about it. We can talk about the glorious past where we had an ATM that was ready for action. But the fact that there's a 0 means that we can't have it anymore. So I guess there's a cake and eating joke. I did not, and so I'll do that now. So yeah. Sorry, I didn't hear that.
What made it become a 0?
Right. Okay. So.
Was the linearity up there in the type that...
I'm gonna go back to the thing that I decided to skip, and I've decided given that you've asked that question, I've decided it was a bad idea to skip it. So I've got what I believe to be a cool example, but I'm more interested. I'd rather get the fundamentals across. So here's a small example. I'll get rid of these. I'll get these out of the way. So it's the duplicate one I'm interested in. So we've seen the quantity 0. So here's an example with the quantity 1. So I've just put the quantity 1 on the type to say that I can use this x exactly once, but I'm going to try to make a linear pair with it. Now, hopefully this isn't going to work. I mean, because we've only got one of it, and I'm trying to make 2. So if I try to generate it, it says no search results. But I'm just going to carry on anyway. I'm going to try to write it. So if I check the type of .RHS now, it says I have exactly 1x. The reason I have exactly 1x is because I said so, essentially. And then once I spend it, so this hash is the constructor for linear pairs. So a linear pair is one where I use both I can use both elements of the pair exactly once. So yeah, if I now check the type of .RHS, it says, well, you can't use it anymore. Sometimes people ask here, what if you put the whole first? And I think they're trying to catch out my type checker to see if it goes left to right, but no, I thought of that. Well, if I have the 2 holes, then it assumes that I want to use it in whichever one I'm currently looking at. So when I'm looking at help, .RHS has an x of 0, and when I'm looking at .RHS, help has an x of 0, but I can't look at them both at once. So it assumes that I want to use it in the one I'm looking at. So that means that in this case, the reason that this M has a quantity of 1 is about the type of the bind operator in this linearity monad. So it's a little bit fiddly to get there. In fact, it involves some type level computation based on the use equal 1 in the return type. But essentially, it's a function type that has that 1 in the right position. Anyway, let's finish writing this program. So I'm just going to call it M throughout, because then we won't get the clutter of the old version. I'm going to try checking the pin, and I'll put my real pin in just to. So what do we get? We get so this is we saw this in the API. The result is this mysterious res thing, and then this calculation that depends on something. Now, I think that's a little bit complicated to have to think about, so I'm going to ask the machine to help me. And I will use a little shortcut to create a case block, so I can do case analysis on intermediate results. You saw me earlier on, I was doing the case split on lists and case split on booleans. So I can do case splits on, I can ask the machine to give me case splits on whatever really. So if I do a case split on the result, it says, well, a result is, it's actually one of those linear pair types that we've just seen. It's a dependent linear pair type. And we can look at the type of the whole to get a little bit more information about what these individual components are. So it says, right, well, the R is the resource, and the resource is going to be an ATM. And what we know about the ATM, well, we're only going to know anything about the ATM when we know a bit more about val. So that's what this asking the machine this question has told us. And then the res that we had before, we can't use it anymore because we've spent it by doing the case analysis on it. I'm just going to simplify it because of what it's told us. I am going to change the names of something. All I'm doing is factoring out the pair here. Yes, sorry, that is what I wanted to do. Yeah, that's what I wanted to do. So I've got my crib sheet. I'm not even looking at it. It's if I looked at it, then this would make more sense. Never mind. Okay, so all I've done is factor out that pair so that it's the code looks a little bit neater. Right. So we now have a machine where the case val, so that's this thing, is unknown, and we've got a case expression on it. And the clue in the type here is that if I do a case analysis on it, that might refine what's going on in the type of the ATM so that I can make more useful progress. So I'll just do a case split on it. So we've now got the two cases. We've got two branches, either the pin was correct or it wasn't. In the case where the pin was correct, it says, great, we've got an ATM that has been validated. We're in the session, off we go. And in the case where it's incorrect, it's still in the card inserted state. So thinking back, way back to the beginning of the talk, where I gave this contrived little example of, I'll just show it again. I got this contrived example of, the type changes depending on the Boolean. That's exactly what I've done here. So I'm reasoning about the two different code paths based on some result that I got from an operation. Now, people sometimes ask here, which nobody has asked, and therefore I'm going to ask it for you, is why not just return an either? So the either type being a type which has two possible values of two possible types. So it either returns an ATM card inserted or it returns an ATM session. So the reason I don't do that here is it's a bit more flexible to not require you to check the result first. So again, I'm told by my cache machine friends, NCR, that you know when you enter your PIN incorrectly, I'm sure you all do this occasionally, and then it carries on asking you questions. So the machine will carry on asking you how much money you want and what services you want, and it's only when it gets to do the actual check that it tells you, oh, all of that stuff you just asked me to do, can't do it. So it carries on prompting you for these things. Apparently the reason for that is that they run on very slow internet connections and they package up all the requests at once. That may or may not be true, but I'm saying it on the internet, which makes it true by definition. So I don't know why I say these things out loud sometimes. Anyway, the point is we can do things in between asking for the result and getting the result. And it might be the same thing depending on the branch. So, and maybe I want to write a message on the machine. Is that the right? This sort of thing. So it just gives a little bit more flexibility to give that dependent pair rather than returning the either. Now, I've got just enough time to show you the bit I wanted to get to, which is about why would we actually want to do this? So this ATM example, I think it's pretty neat that you can define protocols this way that are checkable. These small little examples, but it would be fun to see if we can scale this up to realistic examples with, say, distributed systems or concurrency. So I'll tell you a little bit about session types and how we might represent those using a quantitative dependent type system. So session types, going way back to Kohei Honda in the late 90s, it's a typing discipline that allows us to describe patterns of communication. So you can imagine the state of a channel. So say you've got a protocol where you send a string and you get back an integer, whatever that means. Well, the type of the channel at one end will be, well, I have to send a string and then I have to receive an integer and then I'm done. And I'm not allowed to do any other send any other values in any other order on that channel because the session type tells me what order I have to do things in. So the goal here is to implement exactly that using quantitative dependent types, using this mysterious L monad that I've just kind of sketchily told you about. So the first thing we're going to do is define what it means to be an action on a channel. So this is kind of an embedded domain-specific language for describing communications. So on a channel, we can send something of type A, and then the next thing we do on the channel, I'm going to say that I don't want to map out exactly the pattern of communication in advance. I want to be able to do different things depending on what I've sent. So let's say I send a Boolean, I send true or false. Maybe I want to receive a string if it was true and receive an integer if it was false. So the following thing after I say what type I'm sending, I'll give a function that tells me what the next state of the channel is going to be, and we'll calculate the value of that function when we've sent the value. Same thing for receive. So if someone sends me a value, I will need to decide what to do based on the type of that value. Based on that value. So only when I get the value will I know the type of the rest of the communication. And then a channel is parameterized by the actions that we're going to do next. So this actions that you see in the channel type, it's pretty much the same as the ATM state. It's a bit more complicated, but it's the same idea as the ATM state that can have just those three values. So I need to define an overall protocol. So we'll call this the global session type. So this is the overall pattern of communication that the entire system is going to do. And that is, we say that a client can request a thing, a server can respond with a thing, or we can sequence a protocol. So if I've got a protocol that returns something of type A, and I know how to take that A and get a protocol, gives me a type B, then overall, that gives me a protocol, gives a type B. So it's kind of like a monadic bind. And then when we're finished, that's a protocol that doesn't give me back anything. I'm going to write two functions, one that interprets a global protocol from the point of view of the client, one that interprets it from the point of view of the server. If I really want to, I can prove that these two functions are dual to each other. I'm not going to do that, but it's useful to know that the client interpretation is exactly the opposite of the server's interpretation. And then I'll just define, I'll show you what a protocol looks like. So this is a protocol where a client will send some command to a server. If that command was to add two numbers, then the client will send a request with the two numbers and the server will respond with a number, and then we're done. And if the command was reversed, then the client will send a string to the server will respond with a string, and then we're done. So this is a global thing that tells us what the client and server have to do, and then I can interpret that from the point of view of either. Just to show that we can get we can start having loads of fun with this, I'll show you what a dependent protocol might look like. So maybe I send a number, and that number will be how many more things I'm going to send. So you see this sort of thing. Well, I'm not going to pretend I know much about network protocols. I think you see this sort of thing in, for example, HTTP, where it says how many bytes are coming, how many lines are coming, so you know how many to ask for. So we can encode that sort of thing precisely too. And then we have an API that is similar concept to what you've seen before with the ATM, which is if the channel is in a state where I'm supposed to send a value, then I better send a value. And the next thing we do on the channel is going to depend on the value we've sent. So remember, this next was a function that says what happens next based on the value we've sent. Well, there you go. There's the value that we've sent. Receive is the other way around. You've seen this res type. You saw res in the case of card inserted. Well, again, as programmers, we're not in control of what the other end of the protocol is doing, but we are going to explain what to do depending on what arrives. So depending on the value that arrives, that tells us what we have to do next on the channel. And just like with the ATM, it's really easier to see this in action. So I've got a simpler one here, just so it's clearer what's going on. So I'm just going to send a bool. If or the client will make a request using a bool, and the server will make a response either with a character or a string, depending on what that bool was. Let's comment out these branches. I can't use help again. There we go. So I can, while I'm working through this protocol, I can do anything that's unrelated to the protocol. I can do what I like. But as soon as I do something with the channel, it has to follow the protocol. So we've received a command. If the command was true, then we have a problem because here we go. I like to put errors in just to show that this isn't a video. Yeah, if it was true, then the next thing we have to do is send a character. So let's do that. Oops. Once we've sent a character, that we can't do anything more on the channel. We have to close it. And then the other case, we have to send a string. So again, that choice we made, or that the value that we received, and this if then else is telling us what we have to do in each branch. So each branch of the if then else has a different type depending on the thing that arrives. And even though that thing's only going to arrive at runtime, we can reason about it at compile time. Yeah, question. Oh, that's a good question, and I was going to add. Yeah, let's do that one. There are no uses of linear name chan. So it says you said you were going to use it and you didn't. So was that what you meant by what could go wrong? Or do you mean what could go wrong in the world if I didn't close the channel? Sorry, I didn't catch that either.
Would I be able to do like something arbitrary with the channel, like besides closing it?
Yeah. I mean, would you be able to do something arbitrary with the channel? As long as the arbitrary thing you're doing is not insisting that the channel you're passing is linear. Now the things get a little bit complicated because if you pass a linear thing to a function that says I'm going to use this in an unrestricted way, that's not valid. So you'd have to be. So the type system wouldn't allow that. So I guess the short answer is it depends. I'm seeing hands going up. I'm just going to finish the talk at this point and just go on to the questions because I think you get the general idea. So yes, there was a question over here, I think.
So after you sent a string or a character, is the chan variable is being bound to the result of those two sends, right?
Right.
Is those closed chans? are those the exact same type, and like you could move those closes like after the if, or are those like two separate types? Like, do you mean like close after string or close after char?
Let me try something. I don't think this is going to work. So what I could do is, I love it when I don't know what's going to happen. Let's what I really want to happen here that probably won't work is that it returns me. So because both of these branches return a channel, that it will bind it to this Chan prime. The reason I think it won't work is because they've gone through two different sequences to get there, and we'll have a different history. But let's find out. Yeah, it's not a very helpful error message, but the answer is no, you can't. So, yeah, you know what? That is a really interesting question, and I want the answer to that question to be yes, you can use the channel. And I'll forget that live coding music I was talking about. You have nerd sniped me. Yeah, thank you.
Yeah, are 0, 1 and unrestricted, are 0, 1 special, or can I say, this value can only be used exactly 7 times, for example, or other integers permissible? Or?
Yeah, so for the moment, yes, they are special. I don't think they have to be. So there's some work going on in graded monads, for example, by Dominic Orchard and his students at Kent, where they're kind of doing exactly that sort of thing. Can we have arbitrary numbers? There's some work going on the opposite coast of Scotland to me. So coast to coast, it's a whole like 40 miles away, where they're looking at more general ways of talking about quantities. So I can't quantify over quantities, for example. So I might want to say that something works for all quantities. Now, the reason I haven't done any of those things is because of a lovely concept by, I think, due to Steve Krabnick, called the language strangeness budget, which is that when you add a new feature, or when you're inventing a new language, you have only a certain amount of weird things you can do before users will run off screaming. Now, there are some languages, like, for example, Haskell, where it's more threshold than a budget. Where, but I felt that if I was introducing something new in Idris 2, I should probably keep it fairly simple. But I really want to explore something much more general. That's a great question. I mean, 0 and 1 are, in fact, 0 alone. If we just have 0 and unrestricted, it's already really valuable. Yeah.
So I was going to take this offline, but because you just mentioned this work, I'm assuming it's Granule that you're talking about.
It's Granule, yes. Granule is the language I'm talking about, yes.
I wanted to ask about this actually because, like you said, graded modal types are like a generalization of quantities, but I have had a hard time wrapping my head around whether you're actually able to do things with graded modal types that are not possible in something like Idris 2. Is it just a matter of performance, or?
I think maybe a matter of expressivity. So I could, for example, say that I can use a thing 5 times by having 5 arguments, each with quantity 1, and then a proof that they're all the same.
Yeah.
I don't want to write programs like that, but
Okay.
but it's possible that they are equally expressive.
Okay,
And
awesome. Thank you.
yeah, I imagine you could write something that computes the type with a different number, and I don't know. That could be an exercise for the reader.